Thank you. Hi, everybody. Thanks for having us here at SREcon. I don't know if we'll live up to solving all of the problems, but we'll definitely highlight some of the challenges that we've been having and what we've done at Meta to help improve machine learning development reliability. So I'm Brian Hansen. I'm a PE manager. I help support the set of teams that is Ads ML PE.
And hi, everyone. I'm Yan Yan. I'm a production engineer in the team.
So we're going to cover a few things today. Oh, a little too far. We're going to start with machine learning development and how it is not the same as software development. And we believe that trying to develop it the same way is slowing us down. ML ops and the software development lifecycle, these don't seem to be sufficient when it comes to making ML artifacts because of some of the inherent properties of ML. We'll be talking through some of the challenges and opportunities that we believe requires the creation of a separate and unique machine learning development lifecycle. Then we'll talk about how this is important to the industry at large and this group of SREs and production engineers. Along the way, Yan's going to deep dive into examples around the two lifecycles and work that we've done on our teams to help solve them that's helped really address some of the top challenges we've seen. This has helped improve the reliability of ML development at Meta, and we hope it's useful for this audience and your companies. Quick disclaimer, you're going to hear Yan and I use PE and SRE kind of interchangeably. This is what we call the practice kind of at Meta around caring about production services. I don't think that they're exactly the same thing, but we don't need to dive into the specifics. I think we care, though, about many of the same things. It's how to build and operate our systems, infrastructure, hardware, software in scalable, reliable, efficient manners. And most importantly, hopefully one that's not manual. So let's dive into ML ops. This has been a topic that's come up lately that's really become popular that people talk about. It's about automation, quality, business regulation requirements. But most of what we've seen and heard is focused on best practices in the final steps of the process, when the model is produced and it goes out into the production to be served. This is really important, but we think it's focused too much on the end of the journey. Today, we're going to focus more on the beginning of the journey. And I think this is important, has been kind of ignored because serving is what I like to call the hot path. When you have impact there, your customers feel it immediately. But ML development is more the warm path. You don't feel it right away, but the problems that you have there are going to have long-term impacts to your business. And so you should be solving them as soon as possible. Our team's North Star is to work on being able to fully encompass the entire life cycle of ML artifacts that eventually become production-producing models. How do we get repeatable, reliable processes up front in these artifacts to be able to understand and gain confidence when they go into production that they're going to meet the business needs? And so we work with our partner teams to do this. So you might say, hey, we've got the software development lifecycle. Why do we need something new? So I want to dig into this a little bit. If you take our example here, it's very simple. When you take your source code, you run it through your compiler, it produces a binary. If you do that again, you're going to get the same binary out. If you hold all things constant, you do this 3 times in a row, you'll get 3 of the exact same binary. You can use an MD5 hash to check that nothing has changed the whole way through, that everything is the same. The outputs of software development are reliable, repeatable, and consistent in this manner. It allows you to step through your changes, knowing exactly what you did, what caused that binary to break, and you can step back and get to a known good state. It's a fundamental fact that a lot of our strategies for developing software are built upon. This isn't true with machine learning artifacts. If you take our ML take on this, you would take what is kind of your source code equivalent, be it model architecture, modeling techniques, feature definitions, or some combination of all of those 3, and you combine them together with data to produce an artifact. If you follow that process again, you're going to get a different thing. Sometimes it's a little bit different. Sometimes it's wildly different. Every time. So I think it's really like a key point here is you can train the same model with the same architecture, the same techniques, the same data. You can even go out to the data center and use the exact same hardware, and you're going to get different results every single time. Your MD5 hashes will never match. You'll have no way to recreate an exact artifact. You can't step back and forth between your changes and know exactly which one has made the biggest difference. There's this non-deterministic aspect to ML that we believe requires coming up with new ways of dealing with developing, deploying, and monitoring and scaling them. One that starts the journey with the ML artifacts as they're created and make their way out to production. a machine learning development lifecycle, or ML DLC, that takes into account this variability of ML artifacts. And it should be grounded in the many lessons that this community and others have learned over the years. Now, ML is also built on infra, which should be deterministic, but I think we all know maybe sometimes it's not. As we talk about this, we'll find out a little bit more what we need from this community to also improve the reliability of the underlying infrastructure to help reduce that amount of variability in the ML artifacts. So, the 0 to 1 effort, or creating something from nothing effort, in this space has primarily been done by ML engineers, many of whom are brilliant PhDs with an academic background. They have these really great, awesome ideas, they create experiments, check the results, and they move on to the next thing. And while academic experimentation is meant to be repeatable, it's usually under highly controlled conditions, and its track record is actually pretty low. We took a look around at a few surveys. There's a 2011 survey of medical studies that showed that 65% of them were inconsistent and retested. In 2017, another around peer-reviewed economics journals showed that less than 48% were in compliance. Closer to our subject at hand, there was a 2020 Carnegie Mellon University study of more than 1,500 ML researchers that showed that more than 90% of them believed that there was a crisis with regards to the reproducibility of ML results. So I think it's really interesting. If we had 10 ML researchers here up on stage with us and we asked them, hey, that awesome thing that you made yesterday, could you do it again? 9 of them would be like, I don't think so. Oh, jumping around a little bit. So I think that there is a leap that you make when something transitions from an academic environment into a production environment. You're making the leap from something, proving that something works, to making it repeatable, or at least understandable and consistent. Some engineers, they make something from nothing. Others make that something work 10,000 times a second. And I think this is where SREs and PEs excel. So we believe that we're entering the 1 to 10,000 phase of ML development, where we take these really amazing ML artifacts and we apply our skills as SREs and PEs into making them, or taking them to the next level of scale. I think this is what we're great at and what we actually want to do with our jobs. We take the technology and we turn it into highly scalable, repeatable processes through the software that we build and the knowledge that we share with these people. We create highly leveraged systems with repeatable processes that work within the constraints of ML unpredictability. As an industry, we have a coming wave of ML artifacts and the capacity needed to create them. As we need to prepare ourselves to handle this large influx. PE's role is not just to operate the system, but it's to partner with the folks who are building it, and in this case, it's ML engineers. We make things work 10,000 times a second and beyond. And with that, I'm going to hand it off to Jan, who's going to dive into the 2 life cycles and some of the early days of our team's work.
Thanks, Brian. And now let's start with software development lifecycle, which was pretty mature in 1960s. In general, we have 6 key steps. To start, we have very clear requirements. Then we design the software, followed by agile development. Testing is to check whether all our requirements are met. If so, go deployment. And in the end, we continuously maintain or scale the software and iterate through the process. And now let's see what's different for machine learning development lifecycle. Unfortunately, there's no industry consensus or solution yet, so I'm going to share a highly simplified overview based on our current understanding. First and foremost, there are no specific requirements. We just want better and better results. And we heavily depend on machine learning engineers' research or creativity to come up with new ideas to figure out how to improve machine learning performance. Then we go through design. And after that, unlike software, where we jump into development, we need to do demand planning. Mark Zuckerberg created Facebook on his laptop, but for machine learning, we need data centers. The better machine learning is, the more capacity and the more powerful hardware we need. And after that is privacy, because the soul of machine learning is to learn from data, an ocean of data. Recent years, society has increased its awareness and regulation of privacy. All of us has been working on stricter and safer data usage. Privacy is and will always be a critical step in machine learning. After that is coding, and a key different step, exploration. We need to try all our brilliant ideas and turn research into experiments. We want to be able to know whether they're good or bad beforehand, and exploration survival rate is very low. It's usually like venture capital or gold mining. It will filter out over 80% of the candidates. The rest of them will go into A/B testing. A/B testing is like finals of competitions. Those who win will be deployed, and they will be serving production traffic. In the end, instead of in maintenance, machine learning models will either stay in production as they are, or they will be replaced by better candidates and then be deprecated. Because unlike software whose output is consistent and reliable, machine learning performance may get worse and worse over the time due to infra or data issues. Because, for example, we may not be able to use some data due to new privacy policies. We cannot simply put up a patch to fix it because once it's launched, it's immutable. Oftentimes, we have to start from scratch, or at least from the coding step. So our machine learning users, they have to go through all the steps. However, under the hood, there are actually different services and systems supported by different software engineering, aka SRE teams. Oftentimes, when there are machine learning infra issues, it's common, but actually non-trivial for machine learning users to figure out roughly, okay, which system is problematic and which team should I ask for help or throw my complaints. So as PEs, we highly believe that machine learning users should use their time and talents to improve machine learning performance rather than worry about how to debug ML infra or team structure. So by this, we identify a unique opportunity and value as PE or SRE, because in general, we cover a large area for reliability. We fill in gaps and build bridges among systems and teams. We are very good at monitoring, alerting, and triaging very complex problems. Then we can identify root causes and work with users and infra suites to fix them. So our team has been working towards this goal and supporting the machine learning development lifecycle for over the past 4 years. We identified 3 top challenges over the year. The first one is observability. And now let me share what it was like when we entered this area. So a long time ago, there was no golden list of our production models. In ads, we also call production models as V0 models. No one could answer this simple question. Fantastic V0 models and where to find them? Our machine learning engineers, they were crystal clear of what production models they built. However, it may only existed in their minds or some Google spreadsheets. So it may reduce like duplicate work or missed collaboration opportunities. However, it was impossible to find out because there was no codified or complete production model list. So we can see that it was so, and more interestingly, there were several lists. However, none of them agree with each other. Nor was there sustainable or easy accessed ownership of models. So now you can imagine, whenever there are some incidents about our production models, it was a game of telephone to figure out, okay, who was the right person that had the context and was able to fix the problem. We as PEs at that time, unfortunately, frequently acted as switchboard operators. And now please let me share a story with you. I was on call a long time ago. One day, all of a sudden, I received a lot of alerts. I was completely shocked and stressed. Apparently, something serious happened. So I dug into the problem, and I figured out some possible root causes of some systems and models. I didn't know at that time it was the start of my tortuous journey of finding POCs. In Meta, we have a lot of code bases. So I found different owners from different code bases. However, unfortunately, it was a legacy system and ML artifact. They were not actively maintained. So I ran into the situation that the owner may be no longer employed, or they were on vacation, or they have changed the teams for a long time. And finally, I landed with a new hire who had a little bit more context than me. So although, fortunately, finally we mitigated, but it really took a village. So I think this may more or less resonate with some of your experience debugging systems that lack of clear ownership. And the good news is we have greatly improved the situation with the following solutions. First, we centralized and audited all our machine learning artifacts ownership. Then we synchronize it across different places so they can be consistent. And next, we made company-wide efforts to enforce we must set ownership upon creation. And we set up a general principle that we need to replace owners with on-call rotations to avoid single point of failures. This was what we found the most helpful for organic ownership growth. We also built monitoring, alerting, and auto-escalation. So alerts will go into other people in the on-call rotation, or other team members, or managers, directors, VPs, and eventually Mark, if none of the POC were available. However, only solving the ownership challenge is not enough. Over the year, our team has built a production model service for ads. We own this end-to-end. We designed a data model, storage, built the business logic, and a user interface. This screenshot is just with example data. It has 4 main parts. The first one is top-line metric. It can show our modeling scale, some company top priority progress, for example, migration to PyTorch, and some high-level model healthiness metric, like the number of stale or not training models, the model overall maintainability, and we can easily track our model development velocity or throughput in the months or half of the year. And we're happy that this tool is intensively used internally. We have thousands of distinct users every month. The second part is we link to vital dashboards for more details and in-depth debugging. The third part is that these tools automatically show all the ongoing incidents that are impacting our production models. And in the end, it's the most important part. We show all our production models with their key metrics. For example, launch history. So we can revert to previous versions or check all the revert histories here. We have launch time, which can be valuable to debug with incident timeline. We can show some performance metrics like staleness, maintainability, or revenue importance, and other properties like training type, so we can know whether the model is doing online training with real-time data. So, like staleness, maintainability, and revenue importance, and other properties like training type, so we can know whether the model is doing online training with real-time data or recurring training with historical data, or the model is completely not training, or doing online and recurring training at the same time, which is not expected. And later, we can also see properties like package, architecture, and framework. Our team is also responsible for supporting fallback models. Fallback models will be used if production models cannot work as expected. And we also show owner and on-call information here, so users can quickly find POCs for support or collaboration. Users can easily make a post to ask questions or create a SAF, which is Meta's incident management system, if they observe any abnormal metrics. For example, one user created a SAF because they find over 200 production models were not training. And in the end, we are happy to share that although this project started as an ad solution, many people in other teams find it's useful and general for their use cases. So now we're working with many PE or SWE metamates in AI, Instagram, Reels, Marketplace, Integrity, and many more to onboard them on this tool as well. So our North Star is that we want to make it to be the one-stop shop for all production models. There are 3 major benefits. So to start, having all our production models in one place help us identify and mitigate incidents faster. We can better track company-wide model healthiness and top-line milestones with centralized monitoring and alerting. We can improve transparency to avoid duplicate work and then drive end-to-end machine learning solutions with integrating with other systems. And now let Brian to share more about scalability.
Thanks, Jan. So when we started about 4.5 years ago, we just knew that we had a big bunch of stuff, right? Finding anything in there was very difficult. Either you knew where it was because you built it, or it was causing a large enough fire that it was an all-hands-on-deck situation to go figure it out. And playing a game of telephone when your platform is down is exciting, but it doesn't make for quick resolution, nor low blood pressure. So after the creation of the production model service, we transitioned to having a smaller bunch of just stuff out there, but then a well-structured set of production models where we had ownership, we had key performance indicators that let us know about their health and many other things that were important to the business. This allowed us to be much faster when resolving issues and finding them and resolving them, and it allowed the team to actually start taking on more interesting work as well. We really transitioned from having this kind of tree-level view, if you stick with me for a second here, of going out to an individual model, looking at and see what's going on, to having more of a forest-level view. We could see how the set of production models were working, right, and have the overall health and status of our fleet of these production models. So these fewer fires, they allowed us to get deeper insights and then start focusing on the next challenge, such as capacity. We could start looking at things like multi-region scheduling, data placement, onboarding of new hardware types, which is the challenge in ML, and system utilization. So this brings us to the next one, is capacity. Even with Meta's size and resources available to it, capacity can be a challenge. ML engineers programmatically can make these modeling tries that they do. It's not a lot of additional marginal effort for them to try 100 ideas versus 1 idea. They want to take as many rolls of the dice at this explorative process as possible. And so this turns out to present some major challenges when you have hundreds of engineers all over the world rolling the dice on large numbers of machines across our many different data centers. And so Jan will share some stories around debugging this and solutions for capacity.
Cool. I believe capacity is a challenging topic for all of us. Capacity crunch leads to war rooms and headaches. And whenever our systems are at capacity, we will receive alerts, failures, and user complaints. Our team is responsible for supporting model training. So years ago, we built this dashboard to show model backlog queue. So it tells you how much time users need to wait for their jobs to start training. And as we can see, the queue was huge frequently. So many users were complaining that, all our machines were busy, and their jobs has been waiting for many days. So it was easy to jump into the conclusion that that's because we didn't have enough capacity. We just need to order more, build more data centers. But even for Meta, it's very expensive, and it's a challenge, and it has a long lead time. So as PEs, we decided to take a closer look of our system resource usage. And we were very surprised. As you can see in the first screenshot, over half of our CPUs or GPUs were allocated or busy. And of those, even less of them are being actually used. Then we dug deeper. We found that across our training fleet, more than half of our servers will only use less than 5% of their CPU or GPU power. The rest of the fleet, although they were using more, it's less than 50%. That was far from ideal. And for our memory, almost all of them use less than 30%. Okay, so let's recap our situation. We have jobs piled up desperately waiting for servers. However, all our servers were busy, but only a very small amount of our resources were actually being used. How come? We were really confused, so our team built a tool to figure out why. So the first takeaway we had was that we need to change our lens to look at server resource usage. Previously, all our monitoring treat all the servers all the same and all together, but we actually are doing distributed training in Meta. In general, servers are made into 3 groups and with different responsibilities. We need a group of readers to read input data. We need a group of trainers for computation, and we need a group of parameter servers to store and sync large parameters. We didn't have too much insights or treat them differently at that time. So the first feature we developed is that given a job ID, tell me all the resource usage together with their roles like trainer, reader, or parameter server. And then we figure out why. Depending on their roles, actually they can introduce different bottlenecks like memory, CPU, GPU, or network. Readers are usually memory intensive. Trainers are usually CPU or GPU intensive, and parameter servers are network intensive. And let me show you an example. So if one job uses 30 servers with 1 server bottleneck, all the rest, 29 servers, can be blocked and idle. However, they are occupied, so they are busy, but they're actually not using a lot of resource. So with this feature, we were able to identify bottleneck, adjust the number of servers to improve our resource usage and avoid such bottlenecks. Now you might be wondering, how come we ended up with such bad configurations of hardware setting? And it turns out it's because our machine learning engineers, they didn't necessarily know what hardware they were using. So they just clone a successful and complete job and build upon them. And while the hardware setting may not optimal for their jobs. But in our opinion, PEs should reduce and hide all these hardware complexity from ML users so they can focus on only improving machine learning performance. So as PE or SRE, we identify that it's our responsibility to help to make and improve our ML infrastructure more intelligent and more automatic so we can reduce ML users' workload. So we leverage this tool to find optimal settings by comparing multiple jobs and find the best one. In the end, we didn't order more capacity, but the user wait time was greatly reduced. And we also use this tool whenever we need to migrate to a new generation of hardware to tune the settings. We also work with software engineers to build auto-tuning, which can dynamically adjust hardware setting during the training and according to hardware resource usage. Lastly, I want to share another service my team built. It's called ML Guardian. We use it to further save resources. In short, it can monitor, alert, or stop machine learning jobs before it finishes according to the rules machine learning users set. And let me share 2 examples. On the top is a learning curve of one machine learning job. It should be very smooth. If there are such spikes, it means the job needs debugging and cannot be further used. So we can alert or either directly kill the job whenever we detect such spikes. And on the bottom is another machine learning job's QPS. We have minimal requirements for QPS because we need to process enough data during a period of time. So if we detect such huge QPS job, we should alert or stop the job. And in the end, we are happy to share that this service is very general and extensive. We're working with more and more teams to add more rules. We can combine the rules or exclude them with each other. This service has been saving a lot of resources for us every year. After we made so many gains in improving and saving resource, we need some company-wide evolutions. And now let's welcome Brian to share it with us.
Yeah, as we dug into the system resources and capacity, and I will give all of you a challenge. Any problem that you have, if you give me 5 minutes later in the hallway, I bet I can turn it into a capacity problem. So we want to make sure that we're solving the right issues. We did end up growing capacity, but not because users were telling us that they needed more, but because we could prove through data that they actually needed more. And so we started looking more across different issues of how we could better use these resources. We started out with a base level resource management strategy of team-based approach, which was really easy to start with because we have well-functioning teams. We know what they're kind of working on. It's easy to set up, but it's really hard to maintain. We have a lot of movement inside of Meta between teams. We have a lot of XFN, cross-functional collaboration. And so it didn't work for keeping track of how we were using these resources. We moved to a more project-based approach, which became really useful for collaborative approaches, but it was hard to codify and maintain as projects come, not on a very regular schedule. These days, we're now working more towards an ROI-based approach, right? How can we quantify what the business is getting out of these models, out of these long development cycles that we have to produce them, so that we can make sure that we're putting the right amount of resources behind the right projects, the right people, and balance the fact that even at Meta, capacity is a finite resource that we have, and we have to be able to use it smartly for the business. So learning this work highlighted to us, and maybe it's obvious to everyone, but at the time it was novel a few years back, that this is a really costly, time-consuming funnel process that we're dealing with when developing machine learning models. So ads as an example, we have 10,000 plus exploration jobs running every single day that take many, many megawatts of power, 10,000 rolls of the dice every day to figure out what we can be doing, with the promising ones flowing into A/B testing. That A/B testing, we have thousands of jobs there that have to be compared, monitored against, have long-running experiments to see if they are actually getting the improvements that we want into the ML models. And at any given time, a few hundred of those finally make it out into production, and these become the production jobs that we monitor, we care about in the production model service. To go from one stage to the next, generally speaking, takes months, right? And if anything goes wrong, you have to start over again. Even though Meta started its machine learning journey back in 2014, it's still a really time-consuming process. And a big part of that also, though, happens to be ML reliability. These jobs are very large. They run over many machines. If any of them fail, the job has to start over or start from a more recent checkpoint, and you lose what you're doing. And so it becomes really consuming, and so you care a lot about how reliable the infra is underneath. So, for a platform or service, you set up a reliability SLA. Let's say it's 90%. I know it's not great, forgive me, but it's not terrible either. This is something that's new. We know that machine learning is novel. We're iterating on it quite quickly. So we set a 90% one. We know 10% of the time it will fail. Okay, great. But as I hope that we've made a little bit clear, machine learning is made up of multiple systems combining together to produce these models. And so let's just say that you have 5 systems together, and each of them has this 90% reliability. Well, reliability, I think as this room knows, is not the sum, but the multiplication of those SLAs, right? And so that really means when you take all of these systems together, you only have 59% reliability, and that's in the best case, right? If you're hitting it every single time, you're hitting what you're going for. So what we really want to work towards is how can we improve that overall reliability? And when you take 1.9, you turn it to 2, and you do that math, you're going to end up getting 95% reliability. So I think that this is where this room, this community, can really help support ML development, even if you're not working on it directly, right? By building the infra that you care for, that you take care of, can really improve the overall reliability of the machine learning development process, right? Whether your work is in the data centers, on the traffic, and logging, all of these are needed to generate and store and consume the data for the ML artifacts. Whether you take care of developer or staging or production environments, making sure that they're reliable for the ML engineers. These are all ways that you can contribute to your businesses as they're going on this ML journey without even being in the ML part of the business. It's really important. So the work that we're doing in ML and the work that other folks are doing in infra works with each other. They have impact on each other. And so that's the kind of the next challenge that we're going on to, reliability, and how we can improve reliability, both in infra and in ML. Yeah?
Thanks, Brian, with the math. We are really facing reliability challenges in building AutoML. The goal of AutoML is to reduce user manual work and improve velocity by connecting all the systems and steps across the machine learning development lifecycle. So we can go through one step to another automatically. We are collaborating with software engineers building AutoML infrastructure. We need to develop new features or fix bugs and release them with new packages so our users can use them as quickly as possible. However, the package release is a nightmare. In the beginning, as you can see, we could barely have a successful package build. Not to mention, we have a 2.5 days release SLA. Because the package was too big comparing to our previous services or CLI tools, it covers too many systems and have too many dependencies. It could easily time out or fail even due to transient issues. So we looked into the problem. We checked the process and dependency trees. We broke it down into several smaller stages, and we add more retries and error handling. After that, although we still cannot guarantee our release SLA, it was much easier to debug, and we have more successful builds and releases. Currently, we can mostly meet our release SLA. We mainly did two things. First, we analyzed, identified, and fixed top errors. Most of them came from upstream services. Remember the math Brian just did. Those errors were among the 10% reliability of our upstream services, 90% reliability SLA. We really nudged them to fix it. But because altogether, they resulted in our 50% reliability. So the lesson we learned from this is that to build a highly reliable AutoML infrastructure, we need higher reliable upstream services. Secondly, we added more package tests so we can skip bad release or debug earlier to avoid wasting time. And my team was highly recognized and appreciated by software engineers in this project. What I want to share and reinforce with the audience is that in this project, we are bringing PE or SRE strengths and expertise to help software engineers to better build or scale infrastructure. We don't necessarily need to know a lot about machine learning or AutoML. I believe it is also true for non-machine learning but super complex infrastructure with a lot of dependencies and upstream services. Hope you find our talk so far useful, and now let Brian conclude our talk.
So there's a few things I hope the audience takes away from this. First and foremost, that the outputs of ML development are non-deterministic, and that we should be looking for ways to take that out into account as a feature, not a bug. How we design the development process to creating monitoring and metrics for it. I think there's still a lot of work to be done here. We have not solved it all yet. How can we create an understanding of what is tolerable from an ML model when we don't know that the exact answer that it's going to give us, and that we're getting the right outcomes for the business. And so I think that this is a big space that we can continue to invest in, and I look to see what this community can do with it as well, I hope, and we can learn from you all too. The second piece is we really want a culture of ownership and responsibility at Meta, and I think most people want that too, not one of throwing it over the wall. As PEs and SREs, we have experience that we can share with ML teams to really empower them to operate their models in production environments, which is something that they're not used to. I don't think that the solutions are necessarily that novel that we talked about, but they were to the ML engineers because they're not used to running production services. Those of us in the infra space can help set great examples as major players in ML development, role modeling what it means to run a production service and take great responsibility and care of it. And how we set the tone now is going to set how this space is shaped in the future. And finally, at Meta, we have a core company value that we want to live in the future. And I really believe that the future is AI and ML. It's coming, and it's going to impact every part of this industry going forward, whether our teams use it directly or we support the dependencies upon which it's built. I think this is an opportunity for SREs to evolve with this coming wave, rooted in our deep knowledge and background of running large-scale production services. One of the first things folks ask me when they're looking at our team to considering joining us is, I'm interested in ML, but I don't know anything about it. Can I be successful here? And I always tell them, absolutely. I'm not looking for people to join the team and work with us that have great ML experience. I'm looking for folks that understand what it takes to build distributed systems and make sure that they're well monitored, well understood, and we know what they're doing, and bring that knowledge to the ML. The ML experts, they'll bring the ML to it. Now, I think there is something to making sure that you work with the ML teams and you get better outcomes when you understand what your customer wants to do. So I encourage folks to understand their workflows, what it is that they're trying to achieve, not necessarily what they're asking for, which is usually capacity. And so we're really looking for this opportunity to connect these two worlds more closely together. And so that I think as a community that we can not only live in the future, but all of us can thrive there too. Thank you. I also want to call out all of these people, sorry. This is the entire team that could not be here. This was not Yan and I's work. This is the work of the entire team. They could not be here with us. I wish that they could. Now, thank you all. Thank you.